Begin chapter 8, we're going to look at the hypothesis testing process, and our first section here is essentially going to be practice writing our two hypotheses, a null hypothesis and an alternative hypothesis, and then also finding what we call critical values based on what's called our level of significance. So let's start out with our two hypotheses. Basically what we're doing with hypothesis testing is we're comparing two different sets of items. We're going to compare, for the most part, we're going to compare a population value to a sample value. To start off with, we're going to compare a sample mean to a population mean. Then we'll move on to proportions, standard deviation, and variance. But again, we're comparing or using this sample to evaluate whether a statement can be made is true or false about the population value. So a null hypothesis is, first of all, written as H sub 0. H sub 0 is how it's read. That's our null hypothesis symbol. That null hypothesis states there's no difference between the two groups that are being compared. So for example, if I want to compare the average ACT score for our stats class with the average ACT score for the entire population of Waukee High School, I would write a null hypothesis comparing those two, saying there's no difference between the stats class ACT score and the Waukee High School ACT score. The alternative hypothesis then, H sub 1, would state that there is a difference between the two groups. So maybe I think the stats class has a better ACT score, so I would say my alternative hypothesis says the stats class has a higher than average ACT score, and we would use our hypothesis testing process to evaluate or test that claim. One side note here, very important part, the null hypothesis always contains the equal to sign. So essentially, probably 9 times out of 10 or 95 times out of 100, we'll start out when we look at these and write our alternative hypothesis first, because that alternative hypothesis will state some sort of difference as being less than or greater than a certain number, and then we'll fill in our null hypothesis, just knowing the null hypothesis always contains the equal to sign. So we'll come back to those hypotheses in a minute, but our second definition or terminology here would be something called a level of significance. A level of significance, if we go back to our curve from chapter 6 and 7, our level of significance is that area in the tails of the curve or the chance of making a mistake, what's called a type 1 error. So that, if you recall from our talk back in chapter 7, that area in the tail of the curve or tails of the curve is called alpha. So alpha is our level of significance. You can see that written right here. Now that can vary based on whether we have a one-tailed test or a two-tailed test. You can see here I have both tails in our curve shaded, so that would be a two-tailed test. Once again, alpha is simply the area in the tail of the curve. That's the chance of making a type 1 error, and we're not going to spend a lot of time talking about type 1 error, but I'll just simply tell you a type 1 error is made if the null hypothesis is rejected when it's actually true. So essentially, type 1 error is a chance of us being wrong. Much like in chapter 7 we talked about a 95% confidence interval. There's a 95% chance we're correct, which means there's a 5% chance that we're going to make a mistake. So that's what our level of significance is. So a couple of common ones that we'll see a lot of in our problems are 0.01 and 0.05. We also might have a few 10% ones or 0.10. So that's going to just vary from problem to problem, but those are some of our common levels of significance. And this curve comes important because we'll be using our curves or our tables, table E, table F, and table G as we move through chapter 8, much like we did in chapter 7, based on population standard deviation, sample standard deviation, whether we're working with a mean or proportion, standard deviation or variance. So right here we have 5 steps in our hypothesis testing process. We're going to start out today in this first section by just practicing writing our two hypotheses. So step number 1 is to write our two hypotheses. That will be a null hypothesis H sub 1 and an alternative hypothesis H sub, or backtrack, null hypothesis H sub 0 and alternative hypothesis H sub 1. If we move on to our 5-step process, we'll find critical values. Those will come from our different tables. To start with, when we're working with the mean here in our first section, those will come from Table E. But as we move on to our second section, third section, and so forth, we'll use our other two tables, F and G. But our critical values are going to come from those tables. We'll compute our test values. Those will be our z-scores that we've worked with. So a value, or actually we're working with sample mean. So sample mean minus the population mean divided by the standard deviation of the square root of our sample size. That's our central limit theorem. Number 4 and 5, we make specific statements about our null hypothesis and about our claim. So here in number 4, we're going to either say we are going to reject the null, or we're not going to reject the null hypothesis. So notice step number 4 is a statement about that null hypothesis. And number 5, we're going to make a statement about the claim that we make, and that claim is either going to be supported by our evidence or not supported by our evidence. And we'll see that come into play later on as we look at those 5 steps. And finally here we have our z-score listed. There's our central limit theorem. Just as a quick reminder, our order of operations on the calculator tells us we want our numerator and our denominator in parentheses for that to calculate out correctly. So as we move on here, as I mentioned, the first section here, what we want to do is get used to writing our null and alternative hypothesis. So I'm actually going to start down here as this bottom one and work my way back up and then go to the next ones. So the first one I'm going to work with says a contractor wishes to lower the monthly heating bills by using a special type of insulation in houses. The average monthly heating bill right now is $78. Okay, so right now we're running a null hypothesis based on a population mean of $78 and an alternative hypothesis based on a mean of $78. As a quick reminder, our null always contains the equal to sign, but typically we'll write our alternative hypothesis first. So I read back through here, our contractor is trying to lower the monthly heating bills, which means he wants those heating bills to be less than $78. Now, if that's my alternative, if I go over to my null, the opposite of less than is greater than or equal to, and notice my equal to sign is here, so we've written our 2 hypotheses. We're going to test whether or not they are less than $78, and our alternative says there's no difference, they're going to stay the same or be less than, so we write less than or equal to. We'll write these 2 as opposite statements, even though our textbook is always going to put an equal to sign here. I think it just makes more sense to have these as opposites so we can see the correlation or relationship between the 2 of those. So now as we move up here, it says a chemist invents an additive to increase the life of the automobile battery. The mean lifetime right now is 36 months. So our null hypothesis, we're working with a mean of 36 months. Our alternative hypothesis, we're working with a mean of 36 months. Our additive is supposed to increase the life of the automobile battery, so it means it can be more than 36 months. Opposite of more than 36 is less than or equal to. So again, noting our null hypothesis contains the equal to sign, so we're less than 36 months. So we've written our 2 hypotheses. One more time here. A medical researcher is interested in finding out whether a new medication will have any undesirable side effects. Researcher is particularly concerned with the pulse rate of patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? The mean pulse rate is 82. So our null hypothesis is based on a mean pulse rate of 82. Our alternative hypothesis is based on a population mean of 82. Now right in here it says he's not sure whether it will increase, decrease, or remain unchanged. He just thinks it's going to change or be different, so we're going to put not equal to and equal to here. So there's our 3 options. Just kind of backtracking here. This is considered to be a 2-tailed test because we have the not equal to. It can be less than or it can be greater than. This is considered to be a right-tailed test because we're greater than 36, which means then this is considered to be a left-tailed test because we're less than 78. So as we move forward here to our 5-step process here in a few minutes, we're going to test or shade our curve based on this alternative hypothesis. Not equal to is a 2-tailed test, greater than is right-tailed, and less than is a left-tailed. But before we get to that point, we're also going to do some more practice with writing our hypotheses, but we're going to go a step further and identify a claim as well. So number 1 says, a researcher thinks that expectant mothers use vitamin pills, the birth weight of babies will increase. The average birth weight right now is 8.6 pounds. So our our null hypothesis is based on 8.6 pounds. Our alternative hypothesis is based on 8.6 pounds. And our researcher thinks that the birth weight will increase, so greater than, less than, or equal to. And because our researcher thinks that the birth weight will increase, this is the claim that once we get through our five-step process, we'll go ahead and investigate. So we've identified our claim as well as writing our two hypotheses. A couple more times with that. An engineer hypothesizes that the mean number of defects can be decreased in the manufacturing process of compact discs by using robots instead of humans for certain tasks. The mean number of defective discs per 1,000 is 18. So our average, or our hypotheses, are based on a mean of 18. Our engineer says they can be decreased, so they're going to be less than 18. Our opposite as greater than or equal to. And our engineer is hypothesizing that they can be decreased, so this, once again, the alternative is our claim. And one more time here. The psychologist feels that playing soft music during a test will change the results of the test. The psychologist is not sure whether the grades will be higher or lower. In the past, the mean was 73. So our two hypotheses, based on a mean of 73, null and alternative. Feels that playing soft music will change. Will change means they are no longer equal to 73 and equal to. And since our psychologist feels or claims that playing soft music will change the results, here is our claim. Now the question's probably floating around in your mind is, isn't the alternative always the claim? Well, if I went back to here and I inserted one word into this, so now our psychologist feels that playing soft music during the test will not change the results of the test. Now what the psychologist is claiming is over here, our test results are going to be the same whether we play music or not. So you can see our null could be the claim in this case. Probably, 75, 80, maybe 90% of the time, our alternative will be the claim, but there will be instances where you can see the null is the claim. So there's our start looking at how to write our two hypotheses and also identify the claim. Let's go ahead and go through probably 3 examples here where we go through the entire 5-step process. So here's number 1. Research reports the average salary of assistant professors is more than $42,000. Sample of 30 has a mean salary of $43,260. At alpha equals 0.05, test the claim that assistant professors earn more than $42,000 a year. The standard deviation of the population is 5230. So in step number 1, we'll do what we just did. We'll write our null and our alternative hypotheses. Now as we go through here, we have to be able to differentiate between a population mean and a sample mean. Okay, our sample of 30 has a mean of 43,260, so that's our sample mean. We want to make our comparison to the population mean, and the statement is also made about the population mean because it says it's more than 42,000. So our population mean is $42,000, and it says more than, so that's greater than and less than or equal to. And we're going to test the claim. This was actually spelled out that they earn more than, so over here is our claim. Okay, in step number 2, we first of all identify this as a right-tailed test because of this inequality right here with the alternative hypothesis. So I'm going to go ahead and sketch my curve, knowing that 0 or 42,000 is in the middle. Right-tailed means I'm going to shade this right-hand side. And remember what I talked about, that shaded area is our alpha. You can see alpha here is 0.05. So the area in the tail of this curve is 0.05. Now going way back to chapter 6 and having gotten used to reading this curve, our table E that we're going to look at, I'll mark that on here. Table E measures the area from our z-score on down. So I'm going to go to our table E, and we're going to find not 0.05 but 0.9500 so that we can find the critical value or the z-score that goes with that. Hopefully this is going to come up. oops, I need to sketch out of this and double click on this. There we go. Okay, so I scroll back up here and I'm going to find the value closest to 0.9500, and that's right up here. If I work my way back out, that's 1.65. Okay, so my test score, or my critical value, sorry, is 1.65. And notice on the right hand side, so it's a positive 1.65. Okay, so from there, I'm going to come back to that curve in just a second. But from here, we're going to calculate our z-score, which is going to be our sample mean, which was 43,260, minus our population mean of 42,000, divided by our standard deviation. I'm going to backtrack for just a moment here. The standard deviation is of the population. That's why we use table E. Again, today that won't make much sense, but tomorrow it will, as we look at, or in the next section it will, because we'll use different tables much like we did in chapter 7. But because we have population standard deviation, that's what allows you to table E or a z-score. But going back here, I divide by my standard deviation, which is 5230. Oops. Let me backtrack and try and copy that down the right way. 5230 over the square root of my sample size, and my sample size was 30. So I divide that, or I make that calculation, and I get a test score of 1.32. Okay, so I'm going to take that test score back up to my curve up here. Notice 1.32 is going to fall between 0 and 1.65. If you recall, we shaded here based on the alternative hypothesis. So any test score that lies in the shaded area would say my alternative hypothesis is true. In this case, my test score lies in the unshaded area, which means my null hypothesis is true. So when I go to step number 4, the statement I make about the null hypothesis is, since it's true, we do not reject the null. So we're not rejecting the whole null hypothesis, we're saying it's true. Okay, so there's our two, or one of our two generic statements, kind of a layman's way of putting this. If our test score lies in the shaded area, that means my null hypothesis is true. If my test score lies in the shaded area, that means my alternative hypothesis is true. And my 5th step is a statement about the claim. Well, we just said the null was true, which means the alternative is false. And if the alternative is false, since the claim is the alternative, the claim is also false or wrong. So there is not enough evidence didn't want to do that. Not enough evidence to support the claim. Okay, so there's our entire 5-step process right there. Step number 1, write our 2 hypotheses. Step number 2, find our critical values from the table. Step number 3, find our test score. Step number 4, either reject or don't reject the null. And number 5, support or not support the claim with our evidence. We'll go ahead and go through that a second time here. A researcher claims the average cost of men's athletic shoes is less than $80. He selects a random sample of 36 pairs of shoes from a catalog and finds a mean to be 75 and a population standard deviation of 1920. So population standard deviation tells us to use table E again. Is there enough evidence to support the researcher's claim that alpha equals 0.10? So step number 1, we'll write our alternative, our null hypothesis based on a mean of, pick the wrong number, $80. Here's our population mean. Our alternative hypothesis based on a population mean of $80. He says the cost is less than $80, so less than, greater than or equal to. He claims that it's less than, so over here is our claim. Step number 2, we'll consider this because the alternative right here is less than. It's a left-tailed test. So when I sketch my curve, let's try that again. Sketch my curve on my shell on the left-hand side. So this left-hand area is 0.1 or 0.1000. That's our alpha, or our 10% we see up here. So we'll go to our curve. that will be in the negative side of things. So if I find the value closest to 0.100, that occurs right here at negative 1.28. So my test score, or my critical value, is negative 1.28. Again, we'll come back to that curve. We'll compute our test value here in step number 3. That's 75 minus 80. 1920 divided by the square root of our sample size, which is 36. Didn't put this on the last one, so I'm going to put it here as a reminder. Order of operations on our calculator, put those in parentheses. So we have negative 5 divided by the 1920 divided by the square root of 36, and I get a test score of negative 1.56. So notice as we come back up here, I'm going to put my 0 back in here since I didn't put it in to begin with. But if I bring negative 1.56 up here, it's going to be over here to the left, which means it lies in the shaded area, which is going to change what I do in step number 4, or dictate what I do in step number 4. In this case, we shaded again based on this alternative hypothesis. My test score lies in the shaded area, so we're saying the alternative is true, which the means the null is false, which means we reject the null hypothesis. Okay, so we're saying the null is false, so we're rejecting it. There's our two statements, either do not reject or reject the null. And then in step number 5, since we said the alternative was true, that means the claim is also true. So in this case, there is enough evidence to support the claim. Okay, so notice the difference here. Up here we said do not reject the null, and there was not enough evidence. Here we rejected the null, and there is enough evidence to support the claim. Oh, so there's our 5-step process. We're going to go through that one more time here. The Medical Rehab Education Foundation reports the average cost of rehab for stroke victims is $24,672. So there's our population mean. To see if the average cost of rehab is different in a particular hospital, select a sample of 35, found the average cost of $25,226. There's our sample mean, standard deviation of the population, table E. Is 3251 at alpha equals 0.01, can be included cost. Average cost of stroke rehab is different from 24,672. So number 1 is our two hypotheses based on a mean of 24,672. Null or alternative based on a mean of 24,672. Notice it says is different from right here. Is different from, so it means not equal to and equal to. Can it be concluded the average is different from? So once again, we'll identify our alternative as our claim. But this does change things because that not equal to sign tells us we have a two-tailed test. So I have an area on this side that's shaded, and I have an area on this side that's shaded. Notice that alpha is 0.01. Since alpha is the area in both tails together, that means I have an area of 0.005 on each side. So I'm going to go to the table this time and look up 0.005, which looks like it's right here. And that score is going to be a negative 1.65. Now the good news is we only have to look it up once because our curve is symmetric. So we have a positive 1.65 on the other side. Okay. Oops, let's go back. I think I made a mistake. I think I got 0.05 instead of 0.005. I did. So I gave us some bad information. 0.005 is right here between 0.0051 and 0.0049. So our test scores were not, our critical values were not negative 1.65 and 1.65. They were 2.58 and negative 2.58. Now make sure we can read that table, or I can read that table correctly. Okay, so that allows us to move on to step number 3 and calculate our test value. Our test value is a 25,226 minus a 24,672 divided by the standard deviation, which is 3251, over the square root of our sample size, which is 35. And again, I'll put those parentheses in as a reminder to perform our order of operations correctly. And typing that in, I have 25,226 minus 24,672 divided by 3251 over the square root of 35. And I had a little mistake here, so give me just a second. 25,226 minus 24,672 divided by 3251 over the square root of 35. I get 1.008 or 1.00 or 01. Okay, so my test score is 1.01. 1.01 is going to lie right here between the two of those, which is going to tell me it lays in the unshaded area, so I do not reject the null. And since I did not reject the null, I'm saying the null is true, which means the alternative is false, which means the claim is also false. So there is not enough evidence to support the claim. Now, the process we just went through is called the traditional method of hypothesis testing, the 5-step process. As we move on, we'll look at something called a p-value method and other tables when we move on. But there's our introduction to the hypothesis testing process and the traditional method.